Hi, in this video we're going to talk about algorithm analysis. Basically what we're trying to do here is to come up with a mechanism, a technique, and also a notation that will allow us to analyze the amount of time that it takes to run a particular algorithm based on the numbers of elements that we have on our data. Not only that, but the same technique we are going to use to compare two different algorithms. Let's say that we're comparing insertion sort with selection sort. This is going to be the same mechanism to compare those two. In general, when we talk about the efficiency of an algorithm, we're talking about two things. Either we're talking about the amount of time that it takes for the algorithm to run, and that is called the time complexity, or we're talking about the amount of memory that the implementation of that algorithm requires, and this is what we call the space complexity. Of the two, the one that is more relevant and the one that we're studying in this video is the time complexity. Why is that? Well, because we know that memory nowadays is cheap. 50, 60 years ago, memory used to be a problem, so that used to be a concern. But nowadays, if we run out of memory, we simply buy some more, and the cost of the memory nowadays is very cheap. Now, the time is more relevant because this is going to be actually real time running a particular algorithm. There are different techniques, different ways we could study the time complexity of an algorithm. For example, we could do a mathematical proof. We're not going to do that. We could use what is called a growth rate function. What are those? Well, it's very simple. They are mathematical functions that you are very familiar with if you have done Calculus 1 and Calculus 2. And what these functions do is to measure how the amount of time that it takes to run an algorithm is affected by the increases on the size of the data. Okay, so as the data gets bigger and bigger, what happens to the amount of time that it takes to run a particular algorithm? Is it independent of those increases? Is directly proportional dependent to those increases? So on and so forth. So that's what we're going to study in this video and use the growth rate functions. Before we analyze those functions, let's talk about what other factors affect the efficiency of an algorithm. And yes, there are many factors that are going to affect the time, the running time, but what we need is to come up with an objective way to analyze every algorithm and to compare them. So what are the factors that typically affect the running time of a given algorithm? Well, first is the type of processor, in other words, the type of computer that you're using. If you are running the same algorithm in a computer that you bought 15, 20 years ago, which is not a long time, probably it's going to take much, much longer than if you run the same algorithm in a laptop that you buy this weekend at any store. Okay, so the speed of the processor cannot be part of the analysis. Okay, programming language. Well, the algorithm, the same algorithm following the same specifications, could be written using different programming languages. And given a particular task, it may be that a language is more suitable for that particular task than others. So the analysis cannot depend on the type of programming language. So we're going to ignore the programming language used when we do the algorithm analysis. Coding style, of course, this is going to have a big impact in the efficiency of the algorithms because, as we know, people write the same implementations using different coding styles. And it may be that some styles may be more efficient or less efficient than others. So I'm talking about, for example, people using loops to solve a particular problem, to implement a particular algorithm, and other people using, for example, recursion to do the same implementation of the same algorithm. Or what happens if you have too many tests, or if the tests are independent of each other. In other words, coding style, again, cannot be part of the analysis. The analysis has to be independent of that. And finally, the analysis has to be independent of the status of the data that we are feeding into the problem. Okay, so we cannot consider most of the time what the status is. Is it in a random order? Is it in increasing order? Is it in the opposite order? So when we do the analysis, we are not going to study or consider the original status of the data. This, although, is going to have an impact, and I'm going to discuss this later on, but the idea is that our analysis has to be pretty much independent of these four factors. So what do? There are many solutions, as I said earlier. One is to write a mathematical proof and show that the code is going to do some particular task. But the other solution is to use growth rate functions. Okay, so it's a function that is going to tell us if we increase the size of the data, how does affect the running time of the particular algorithm. And you're about to see that this is not an exact science. Okay, it's just simply an approximation. And what it's going to give us is an upper bound. What does it mean, an upper bound? It means that it's sort of like the worst scenario. So we're going to say, what is the worst that could happen if I double the size of the data? What is the worst that it could happen in terms of running time if I increase the data by a factor of 100? Okay, so let's talk about the growth rate functions. So the first thing is I'm giving you a graph and a couple of things to notice. There's a bunch of mathematical functions here at the end which are placed in order. And you probably are familiar with all of them. You know what log n is, n squared, n cubed, to the n, and n factorial. Then in this graph, I show 5 different growth rate functions. And you see now that I'm using the big O, the capital O, and the parentheses. That's the notation that we're going to use, big O notation. And in parentheses, you're going to see the mathematical function that I just mentioned. You're going to see log n, n squared, 2 to the n, and I didn't graph n cubed and n factorial and n log n. So what is on the horizontal axis? And the horizontal axis is just to give you an idea of what happened as we increment the size of the data. And again, it doesn't matter what this 1, 5, and 10 represents. This could be 1,000, 5,000, 10,000, 50,000, or this could be actually 10, 50, 100 elements in the data, or this could be 1 million, 5 million, 10 million elements, items in my data, in my collections of values. It's just to show you that they are increasing. So what happens as we increase the size of the data? The vertical axis gives you an idea of the time that it takes to run a given algorithm. So at this point, it doesn't matter which algorithm was used to generate these growth rate functions. It's just to give you an idea of what happens to the amount of time. And again, this could be milliseconds, or this could be seconds, or this could be minutes. The idea is that this will be 1 minute, 10 minutes, 100 minutes, or this could be 100 milliseconds, 1,000 milliseconds, 10,000 milliseconds. So they are increasing as we go up. If we move to the right, we increase the size of the data. What happens to the amount of time that it takes to run that particular algorithm? And obviously, as we move up, it's going to take longer. All right, so let's start with this red one, which is log n. Okay, so log n is this red line here. And the thing to notice is that actually is below this horizontal line where the 1 is. And that means that for very small values, this is going to be below this line, which means it's going to be slower if I compare it to other algorithms. But at one point, it crosses the line and then it grows. But notice that as we increase the numbers of elements, as we move to the right horizontally, the increments vertically are very, very small. So it is growing, but at a very small rate. So that's log n. Now, what happens to n? N means directly proportional to n, where n, by the way, is the size of the data. So this will be this green line. So it's not an exact vertical diagonal line as you would expect for directly proportional, because again, this graph is the outcome of running a particular algorithm, so there are some variations. But pretty much, if you pay attention to the green line, is sort of like a diagonal. So it means as I increase the size of my data, as I move to the right horizontally, I expect the same type of increments vertically going up. So increasing the size of my data will produce proportional increases in the amount of time that the algorithm takes to run. So we say it's directly proportional to the size of the data. Let's go to the purple line. The purple line is this one here, that is n squared. And now what we notice is that as we increase the size of the data, we move to the right. There are major significant jumps, increases on the amount of time that it takes to run the algorithm. So it's not longer proportional to n, it's proportional to n squared. So Small changes in the size of the data produces larger changes in the amount of time that is going to run. And obviously, at this point, let's say that we have studied these three, right? The red line, which is log n, the green line, which is on, and the purple line, which is n squared. So if I were to compare three algorithms, one algorithm that behaves like the red line, another algorithm that behaves like the green line, and another one like the purple line, then I'm going to say, or I could conclude, that the one that was used to generate the red line is a more efficient algorithm. Why? Because producing or incrementing the size of the data in large amounts produces very little increases in the amount of time that it takes. The same changes affect the green line in a more dramatic way. Increasing the size of the data is directly proportional to the amount of time. And obviously the purple is even worse because, okay, the same changes are going to, in data, if I go from 10 to 50, here there is a small jump. To go to the green line is a bigger jump, okay, but definitely smaller than going to the purple line. So imagine tracing a vertical line here, okay, for the number 50. Well, this one will take the less amount of time. The green line will be somewhere in between, and the larger amount of time will be purple. Notice that I'm talking about larger, smaller amount of time. I'm not talking about 15 seconds or 100 seconds concretely. This is just an approximation. What about blue line here, O to the 1? Well, that's the horizontal line here. What does it mean, O1? O1 means that it's constant. So notice, as we move to the right, we are increasing the size of the data. But on the vertical axis, it's totally horizontal. It never grows. So the amount of time is independent of the increments in the data. So we say that O1 is constant, meaning that in that particular algorithm, increasing the size of the data will not increase the amount of time that it takes. And again, very important to understand that this one doesn't mean that it takes 1 second or 1 millisecond. The one is simply to show that there is no n, where n again represents the size of the data, is constant. The other thing that is important is to sort of learn this line here because it shows you the relationship. N is the size of the data. So something, if you find an algorithm and you determine that the growth rate function that describes the algorithm is log n, and then you have another one that the growth rate function that describes the behavior of the algorithm is n cubed, well, obviously log n is a much, much smaller value than n cubed, and therefore we can conclude that the algorithm that has a growth rate function of log n is more efficient than the algorithm that has a growth rate function on n cubed. So these things are in order. So this less than means that is for the same n and different algorithms, an algorithm that is directly proportional to n is going to be obviously a lot faster than n factorial. So when we compare two algorithms or two different implementations of the same algorithm, we use these relationships that we have. So let's talk about big O notation. Okay, the big O, by the way, is on the order of. So we generally don't say this algorithm behave on the order of. We simply say the big O notation is what. So O1 we call a constant. If you change the size of the data, that does not affect or does not produce any changes in the amount of time that it takes to run. So we said it's constant, or we said it's independent of n. Then log n is called logarithm because increasing the size of the data is going to produce increments similar to the log n function in the running time. One thing, I'm saying here log n, it doesn't matter if it's log base 2 or log base 10 because it will be the same approximation. Of course, then we have linear, which means it's directly proportional to n, quadratic, which means proportional to n squared, cubic, proportional to n cubed, exponential, proportional to 2 to the n, and factorial is proportional to factorial. And again, this order that I'm showing you here is similar to the order that you saw in this line here above, okay? So algorithms that we say has a big O of 1, okay, when we analyze its efficiency, are the fastest algorithms that we can get. Next will be, for example, algorithms which are proportional to the size of the data. And of course, when we get into this part here, these are pretty bad algorithms in terms of the amount of time. So anything that is quadratic, cubic, or exponential will be very slow for large amount of data, and definitely the worst that can happen to us, and it will take a very, very long time, it will be n factorial. Okay, I encourage you to take your calculator and figure out the actual value of all these functions that you see here for, let's say, a value of 100,000, and then do 1,000,000, and then do something like 10 million, and then see how these values change dramatically. So it's very important to understand that there's a big difference between something that is directly proportional to n and something that is quadratic or cube for the same values of n. So how do we use this big O notation? Okay, so first, the big O doesn't tell us the exact amount of time that it takes for the algorithm to run. That's not what we're talking about. What it tells us is something about a relationship between the size of the data and the amount of time that it takes to run the algorithm. Specifically, how the running time is affected by increments on the data. Okay? Obviously, as I just said, it's not an exact science, it's an approximation, but it provides an upper bound in the sense that this gives us like the worst scenario. What is the worst that it could happen to our algorithm? When you analyze an algorithm, it may be that you have different pieces. It may be that one method calls the second method. It may be that you have nested loops and that kind of thing. So the analysis goes as taking a look at your code, and it may be that in the case of a method that calls another method, well, you need then to determine the efficiency of the method that is being called, and then the efficiency of the method that calls the second method, and then do some sort of comparison. So in general, you could say, oh, I determined that my algorithm is actually n, which is size of the data, times k is a constant. So what we say is, well, doesn't matter what the constant is, this is still directly proportional to the size of your data. Now, you have two algorithms running one after the other, and the first one is On and the second one is On. What will be the analysis of the two algorithms put together? Well, then it will be On. Now, if you do something like this, one piece of the code is On and the following piece of the code is log of n, what is the whole big O notation for the entire code? Well, that will be On. And why is that? Well, because if you look at this, n takes longer than log n, and again, we're providing an upper bound, so we said, okay, the more dominant factor will be this one. Same thing here. Let's say that you call a method and you decide that that method is better described using n squared, and then you call a second method that is On. So if you were to call the two methods in a row to get sequentially, what is the order of magnitude? What will be the efficiencies of those two? Again, the dominant factor is n squared because n squared means that it will take longer than n. So we ignore the n and we say that is n squared. Now, it could be now that you have something like two embedded loops, and then you decide that the outer loop has an efficiency of On, the inner loop has also an efficiency of On. So what about the two loops? What is the efficiency of the two embedded loops? Well, that would be then On times On, which is n squared. Now let's say that for whatever reason you have a loop that again you decide that is dependent on directly proportional to the size of the data, and then in that loop there is some operation that it takes log n. So now we said, oh, the log n portion of the code is going to be executed multiple times because it's embedded in a loop. So this is On times n log n, and that's what we have in here. So in general, assuming that, let's say that this is an equation, a function that is the growth rate function, if you were to do this using heavy mathematics. Okay, then what do we do? Well, the first thing is to say, oh, I'm going to ignore this 5 because that is not even dependent on the data, so that's not relevant for my analysis. And then here, I have minus 2n, but in front I have an n squared. So the dominant factor is going to be n squared. So I start by saying, all right, so now I'm looking at big O of 5 times n squared because I'm going to ignore the smaller terms. And then, as we did in here, I'm going to ignore the constant, so I ignore the 5, and then I'm simply going to say, oh, whatever algorithm I'm trying to describe with this growth rate function has a big O notation of n squared. It's proportional to n squared. Now, what about larger data? Well, first, in order to use big O notation, in order to use this big O analysis with the growth rate functions that I just described, you need to think in terms of big data. What does it mean? Well, let's go back to the graph and notice, for example, in particular, the red line. Okay, so in theory, look at this line. In theory, this is saying that anything that behaves like log n is going to take longer than anything that is independent of the size of the data. But look at this portion of the graph. Okay, here close to the 5, the red line is below the blue line. The red line represents log n. The blue line represents constant time. It's a horizontal line. So around this value 5, we're saying that log n is faster than constant time. Well, 5 is probably 50 elements, 5 elements, 500 elements, 5,000 elements. And that's very small when we talk about real-life data. Once we cross this point, the 10, so you see that the graphs really is compatible with the theory. Anything that behaves like log n is going to take longer time to run than anything that is constant, which is the horizontal line. So we have to think about sufficient larger values of data to see how the running times are affected by the changes on the data. So that's the scalability that I'm referring to down here. I'm talking about, always think about in terms of big data, hundreds of thousands, millions of elements. The other thing that we can do, and I'm not going to do it here, is we can do a secondary analysis. I'm going to use growth rates, I'm going to use big O notation, but now I'm going to use what is called the best, the worst, and the average scenario. And this has to do with the state of the data. So, for example, best case is when the algorithm performs the fastest. Under which circumstances a particular algorithm will perform at its best? When will it be the fastest? So in the case of sort, for example, it could be that the data is already sorted. Think about searching, and the value that you're searching is the one located at the first position of your data, so you will find it very fast. On the other hand, we should talk about the worst case scenario, which is, again, what is the case in which the algorithm will take the longest amount of time or the slowest amount of time, all right? And again, we could think about searching a value that is not there, or sorting something that is in the reverse order that what we want. When we use big O notation, when we do this analysis, most of the time what we're talking is about the average case. So it's not the best scenario, it's not the worst scenario, it's what we call the expected running time. So when you see the word expected running time, or you hear me saying expected running time, I'm talking about the average amount of time that it will take to run. So let me finish this video by just simply mention to you that there are other notations in addition to big O. There is something called big omega and big theta, and they are commonly used in addition to big O. I'm just going to say that big omega, instead of being sort of like an upper bound, is a lower bound. It represents the minimum amount of time required to run an algorithm, and theta represents both of them, both the worst and best scenario, the maximum and the minimum amount of time. You can look this up in Google, but again, most of the time what we do in computer science is to talk about big O notation.